10.5 part 2. This is the Lenz's Law part. So EMF, or remember voltage, is produced when there's a change in magnetic flux through a loop. And since magnetic flux is B A cosine phi, you could change the magnetic field, or the area of the loop, or the angle the loop makes with the magnetic field. No change in flux, no EMF. Experiments and mathematics show that the EMF equals negative change in flux over change in time for a loop of wire. If there are more than one loop, we'd multiply that by the number of loops. That gives you Faraday's law of electromagnetic induction. EMF equals the number of loops times the change in flux over the change in time. N is the number of loops, magnetic flux, time. Remember, magnetic flux is BA cosine phi, where phi is the angle between the loop, the normal to the loop, perpendicular to the loop, and the magnetic field. Changing any of those. All right, so we have a coil of wire. Number of loops is 40, and it carries a current of 2 amps and has a radius of 6 centimeters. The current is decreased at 0.1 amp per second. Inside this coil is another coil of wire. It has 10 loops, and its radius is 3 centimeters. So we have the blue wire for this one, and the yellow wire, I think it's yellow, for that one. Their faces are parallel. What is the average EMF induced in the smaller coil during 5 seconds? Well, I need to find the expression for the B field first. Now, it's the blue outer loop that has the current. So we're going to use it to find the magnetic field. So loops of wire, so we use the magnetic field for loops of wire. Remember, R there is the radius. So at the beginning, it has 2 amps of current. So we fill it all in. We've got our number of loops. Right. We have our loops. We have the mu0. We have our current. The radius is 6 centimeters or 0.06 meters. But then at 5 seconds, our current has actually decreased some. So here you can see the current's going down. It goes down 0.1 amps every second. So after 5 seconds, it's gone down 0.5 amps. So at that point, we only have 1.5 amps. So that's the magnetic field after 5 seconds. So now let's find our fluxes. At 0, remember flux is B A cosine phi. What happens since these coils, these loops, are parallel to each other, the magnetic field from the outer blue coil is coming up through the center of the coil, which means it's also coming up through the center of the inner yellow loop. So the angles between that magnetic field and the normal to the loop, well, the normal to the loop is also coming straight out of the paper. Magnetic field is coming out of the paper, out of the screen. The normal is coming out of the screen. The angle between those are 0. So we have our B. The area is pi r squared, and the angle is 0. After 5 seconds, we use the other magnetic field, the magnetic field after 5 seconds. Everything else is the same. And we have that flux. So our EMF is negative N, and the N would be the loop that we're trying to find the EMF on, so that'd be the inner yellow loop, so we're going to put a 10 for that. Our change in flux, well, that's these two from up there. We'll subtract those. And our time, change in time, said was 5 seconds. Which gives us that answer, 1.18 times 10 to the negative 6 volts. Lenz's law. So that was Faraday's law. Lenz's law tells us the direction of this current. The induced EMF resulting from a changing magnetic flux has a polarity that leads to an induced current whose direction is such that the induced magnetic field opposes the original change in the flux. So the flux wants to stay the same. So the current will create a magnetic field to oppose the change in flux. So determine whether the magnetic flux is increasing or decreasing. Find what direction the induced magnetic field should be to oppose the change in flux by adding to or subtracting from the original field. So if the flux is decreasing, you want to add. If it's decreasing, you need to add. If you would subtract if the flux is increasing. Having found the direction of the magnetic field, use the right-hand rule to find the direction of the induced current. So that's the one where you curl your fingers and your thumb points the direction of the current. Since these are loops, you'll curl your fingers the correct direction to the center of the loop, and your thumb will show the direction of the current. A copper ring falls through a rectangular region of a magnetic field as illustrated. What is the direction of the induced current at each of the 5 positions? Position 1 has no magnetic field, and it's not entering any. There's just no magnetic field. That means there'll be no change in the flux, so there is no current. Position 2, you are going from 0 magnetic field, 0 flux, to some flux as it enters the magnetic field. So our magnetic field is increasing, and thus our flux is increasing. So that means since it's increasing flux, we want to go the opposite direction. So the magnetic field on the screen is going into the screen, so the induced magnetic field must be the opposite way, out of the screen. So we grab this with our fingers coming out through the middle, and your thumb will point the direction of the current. You can see it's going to go counterclockwise. At position 3, there is no current because the flux is not changing. The magnetic field is constant, the area is staying constant, it's not twisting, so the angle stays constant. There is no current. Position 4, the flux is decreasing because they're going from the magnetic field to no magnetic field, so the flux is going down. So we want to oppose that decreasing, so we need to have our induced magnetic field go the same direction as the one that's there, to try to keep our flux the same. So it's going into the paper, so grab your ring so that your fingers are going into the paper, and your thumb points the direction of the current, and it'll go clockwise. Finally, position 5 has no current because there's no magnetic field. It's not entering or leaving any. The flux is not changing, so there's no current. And that's it for today.